Today I will prove the Bernoulli's equation. The Bernoulli's equation is the conservation of energy applied to a fluid particle between 2 points on the same stream. For the equation to be true, if height increases, then pressure decreases and velocity increases.
So here's my game plan. I will prove the Bernoulli's equation by measuring the height in which water sprays out of a pipe and then working my way down to a stagnation tube in which I will prove the pressure at that point. I will also prove that the velocity should increase as the height increases. Here I have drawn my setup. I have a 3/4 inch pipe connected to a pump, which is really just a hose. I have a stagnation point in which I labeled as point 1. When the water is turned on, it will rise up the tube and spray out the top. I marked the point in which the stagnation tube waterline rises to as point 2, the end of the tube as point 3, and the height at which the water sprays to be point 4. I also added a gauge to measure the pressure at point 1 to further validate my answers. So to begin, I went ahead and already marked the points to which the water sprays out and the height of the water in the tube. I also want to show you my stagnation point in which I painted black to be seen easier. I will now turn on the water to prove that the water reaches all my marked points. Beginning with my calculations, I will use the Bernoulli's equation from point 4 to point 3. Known and measured values are P4 equal to 0 since it is atmospheric, Z4 equal to 15.5 inches or 0.3175 meters, V4 equal to 0 since the instantaneous velocity of any projectile at its maximum height is 0, P3 equal to 0 since it is atmospheric, Z3 equal to 12.5 inches or 0.3175 meters, gravity is equal to 9.81 meters per second squared, and the specific weight of water is 9,800 Newton per meter cubed. For calculations, you will start with the Bernoulli equation, plug in the numbers, and solve for the velocity at point 3. This comes out to be 1.2227 meters per second. For my second calculation, I will use the Bernoulli's equation again, but this time I'm going to use it from point 3 to the stagnant point at 1. New known and measured values are V3 equal to 1.227 meters per second, Z1 equal to 0 since that is the lowest point in my project, V1 equal to 0 because it is a stagnant point, and then we start with the Bernoulli's equation again, plug in our numbers, but then this time we will solve for the pressure. This comes out to be 3,858.26 Pascal or 0.55997 psi. To prove the Bernoulli equation, I will use the hydrostatic equation from point 2 to point 1. New known and measured values are P2 equal to 0 since the end of the tube is open to the atmosphere, and Z2 equal to 15.75 inches or 0.4 meters. You start with the equation, plug in the numbers, and solve for the pressure at point 1, which equals 3,920 Pascal or 0.5689 psi. If you compare the pressure found from the Bernoulli's and hydrostatic equation, you get an error of about 0.00893 psi, which is close enough to call this project a success. To further prove this pressure, here's a photo of the pressure gauge. You can't even tell it moves since the pressure gauge has such dramatic jumps, but it is no longer touching the bore, so I'm going to assume it's getting a read of anywhere between 0 to 1, which further validates Bernoulli's equation. Now we're going to prove our second part using Bernoulli's equation from point 3 to point 1. We have one new found value, which is P1 equal to 3,858.26 Pascal. We plug in our numbers into the equation and solve for V1, getting a velocity of 0.0002654 meters per second. So as you can see, if you compare the values found at point 3 and point 1, it agrees with the principle, proving our point that as height increases, then the pressure decreases and the velocity increases.